Okay, well, if there aren't any more administrative questions, then I will tell you, first of all, I'll tell you kind of what combinatorial commutative algebra is about. So there's kind of two ways in which you can look at this. Basically, the point is that this is the intersection between combinatorics and commutative algebra. What does that mean? Well, that means, for example, that we're going to study objects in commutative algebra, such as commutative rings, using combinatorial techniques. And the other thing that this might mean is that we might study combinatorial objects by going over to algebra and doing stuff there. So it'll be just a real interchange between combinatorics and commutative algebra, and we'll be going back and forth, and then both things will be helping each other out. The more that you advance in this subject, the more that you see that things appear naturally. Right? Topology is going to appear naturally, polytopes are going to appear naturally, and so I will teach you everything you need to know about these things. And then there's other subjects that come in naturally that we won't have time to do because basically they're more advanced things. So for example, algebraic geometry can play a very special role here, but we won't really be getting into that. But if it's something that interests you, then that's something you can explore for the project. For example, there are some ways in which numerical analysis comes into combinatorial commutative algebra, and so if you're interested in numerical analysis, then I can suggest some projects for you to go in that direction. Okay, but like I said, this is an algebra class, and whatever we need from these other areas, we will be doing here. Okay.
Federico?
Yep.
Approximately how long after the in-class lecture will the lecture be available online?
Generally, the lecture is online immediately after class,
Okay.
except not today.
All right.
We're setting things up for this semester, but I think by Wednesday that'll be true.
Okay.
And generally, if I remember, I just finish class, I go upstairs and I scan the lecture notes, so that means that they'll be up there right after class. Okay, any other questions? So, the first topic that we're going to talk about is something called Grosvenor basis. Grosvenor bases are a tool to actually do commutative algebra explicitly. So let's just recall a couple of definitions that you guys are familiar with. So for example, what's a ring? Well, a ring is a set that we're going to call R together with two operations of addition and multiplication. And you should have the following properties. First of all, that if you forget about multiplication and only look at addition, then that's going to be an abelian. The second property that you need is that multiplication should be associative. And the third property that you should have is that addition and multiplication should be distributive. And I should tell you that in this class, as you can tell by the second adjective of the name, basically things are going to be commutative throughout almost the whole class. So unless I say otherwise, we're going to assume that multiplication is commutative also. And we're going to assume that you have a 1, a multiplicative unit. Multiplicative identity 1. Which I think is good news for us, because I'm sure you know and you remember that there's strange rings, but the good news is that we won't be dealing a lot with them. Actually, a lot of the rings that we'll be dealing with are actually rings of polynomials. Nice rings that we're very familiar with. Okay? So that's a ring and an ideal of my ring R is going to be a subring of R such that, when I write ST, I mean such that, when you take an element of the ideal and you multiply it by anything in the ring, you stay in the ideal. Now, generally I have to say this for both right and left multiplication, but like I said, we're basically going to be commutative this whole semester, and so that's not too much to worry about.
I there, right? I something like
I am sorry, yes. Thank you. If I multiply something in I by something in R, by just anything, right? If I multiply an element of the ideal by anything, I stay in the ideal. Okay, so these were two old definitions, and so let me give you a new definition. Definition: a commutative ring with a 1 is Noetherian if every ideal is finally generated. This word Noetherian is not really an English word. Maybe it is now, but this is after the mathematician Emmy. I don't know how to pronounce her last name. Noether? Noether. But yeah, so a Noetherian ring is one where no matter what ideal you take in there is going to be finally generated. And what I mean by this is that for any ideal I, you can find finitely many elements that generated. Let's say A1 up to AN. So I is generated by A1 up to AN, which means that when I consider all the things of the form A1 R1 plus plus AN Rn, where the Ri's are my ring, then I can get every element of the ideal as a combination of the ANs. That's my definition of Noetherian ring. There's an equivalent definition, which is that R is Noetherian if and only if we have the following property. It satisfies what's called the ascending chain condition. And what this means is that if you have an ascending chain of ideals, like this, then this thing cannot grow indefinitely, in the sense that if you have an infinite chain of ideals, you have to be stagnant at some point and hit the same ideal and stay at that ideal from there on. In other words, for some n, we have that in equals in plus 1 equals in plus 2, etc. So you can't have an honestly increasing sequence of ideals that's infinite. Okay. Now, for the proof of this, I want you to see the forum, and I want someone to post a proof of this. This is kind of tangential to what we're doing right now, but I want us to just discuss this on the forum where this is. But this is the definition that we will be working with mostly. Okay. So what are some examples? Every time that I give you a definition, I should give you an example of what an Noetherian ring might be. Well, for example, if you go back to remember what we did in the class before this one, there was something called a PID, or principal ideal domain. What did that mean? That meant these were domains where every ideal was principal. And if we remember what principal ideals are the ones that are generated by a single element. So what we have here is that every ideal is generated by a single element. That's a finite number of elements. And so that means that any principal ideal domain is going to be Noetherian. And so, for example, any field, or for example, beauty, which are two of our these are some of our favorite examples of rings. So that's an example of what a Noetherian ring might look like. I should also give you an example of what a Noetherian ring doesn't look like. So can anyone think of a ring that is not Noetherian? If you think about what that means, that means that you need to be able to build a lot of structure inside. For example, you need to have infinitely many ideals that live in there that are kind of increasing. So at least you know that means that's a large ring. That's the first way to think about it. So we might try, for example, polynomials. Or that is the ring of polynomials Noetherian? Well, that's going to be my next theorem, actually. That rings of polynomials are Noetherian. Okay. So that's not big enough somehow.
What the rationals?
The rationals are a field. And so that means that they're not, that they are Noetherian also. We need to be bigger than that. It's not easy to come up with an example, but here's an example. The field of, the ring of polynomials in infinitely many variables. Sounds big, right? So you allow yourself polynomials in an infinite number of variables, x1, x2, up to nothing, up to infinity, right? So these are Noetherian, but this guy is not Noetherian. So how do I show that to you? Well, so far I have two options. I can either give you an ideal that's very big in the sense that I cannot generate it finitely, or I could give you an infinite chain of ideals that's increasing. Can you think of one of these things? For example, what I could do is, I don't know. For example, let's take the multiples of x1. So that's an ideal. And that's inside the ideal generated by x1 and x2. Inside the ideal generated by x1, x2, and x3, etc. I claim that, well, first of all, this looks infinite, but I claim that no two of these guys are equal to each other. How do I know, for example, that these guys are not equal to each other? Well, because x3 lives here and x3 doesn't live here. So this is really a strictly increasing chain and it's infinite. So that means that this guy cannot be nothing. So that's why. Okay. So I want to leave this here, but let me erase this stuff. And let's prove the first big theorem about Noetherian rings. It's called Hilbert spaces. Hilbert spaces theorem says that if a ring R is Noetherian, then the ring of polynomials with coefficients in R is also Noetherian. Hilbert spaces theorem. By the way, you should realize then that a nice corollary of this is that the ring of polynomials in one, given that this guy is Noetherian, you could add a second variable and say, okay, now look at the polynomials in x and y, and that's also going to be Noetherian, and in 3 variables, etc. So this is going to imply that the ring of polynomials in variables coefficients in R. If you iterate this a finite number of times, then you're Noetherian, but somehow you cannot go to infinity. Okay, so how do you prove something like this? Well, I'm going to take an ideal, and I'm going to show that it's finitely generated. So, let I be an ideal. Now, I need to show that this guy is finally generated here, and somehow at some point I'm going to have to use that my ring that I start with is Noetherian. My ring of coefficients. So somehow what I'm going to have to do is take an ideal of polynomials and somehow say something about, to use this, I'm going to need an ideal of coefficients. And if you think about this for a second, you might think of the following idea, which is that I'm going to define an ideal called LC of I. And this is going to be the set of leading coefficients of polynomials in I. So I call it LC. Maybe you want to think about an example while we do this. So for example, let's consider the ideal generated by, I don't know, 4x cubed plus 7x to the 6th and 6x to the 5th plus 11x to the 6th plus 8. So this is some ideal, and now I want to make some other set, which is the set of leading coefficients of the things that appear here. So for example, here's a polynomial in I, so that means that 4 is going to be a leading coefficient. Here's another polynomial. Sorry. You can see see that I'm used to thinking about power series because I'm doing it backwards. So let me change things around a little bit. By leading coefficient, I mean the one of the biggest degree. So, right. So for example, 4 is the leading coefficient. 6 is the leading coefficient. That's not it, right? Because I have to consider every single polynomial in this ideal. So for example, if I take the subtraction of 6 of this polynomial and this polynomial, I get some other polynomial in this ideal, and that's going to have leading coefficient 2. So that means that 2 lives here also. And I basically have to imagine doing this for every single polynomial in the ideal, and I'm going to get something. Okay? All the leading coefficients. So my first claim, is that this is an ideal. It's an ideal inside R. This is an ideal in R. Okay. Why is this true? Well, I don't know, let's say that we have to check two things. We have to check that it's a subring, and we have to check that it's an ideal. So to check that it's a subring, what we do is we say, okay, well, if A and B live here, then somehow I have to justify that their sum is in there, that minus A is in there, that their product is in there, etc. For example, how do I show that if A and B are leading coefficients, then A plus B is also a leading coefficient? Well, let's say that if A is a leading coefficient, then I have to have some polynomial A x to the something plus B x to the something, etc. that lives in my ideal. And if B lives here, then I have to have, sorry, I shouldn't use B here. Let me call these, trying to make a simplified notation, but that was too simple. Let's call it A1 to the A1 plus A2 x to the A2, etc. Let's call this A because it's the leading coefficient. And then G is going to be B x to the B1 plus some B2 x to the B2, etc. Okay. That's what it means for A and B to be leading coefficients. Now I have to invent a polynomial that has leading coefficient A plus B. How do I do that? Well, basically, if I multiply this guy by x to the B1 and this guy by x to the A1, and I add those, I'm going to get what I want. So, let me go over here. If I compute x to the B1 f plus x to the A1 g, then I'm going to get a x to the A1 plus B1 plus A2 x to the A2 plus B1, etc. plus B x to the A1 plus B1 plus B2 x to the A1 plus B2, etc. So then if you look at this, you notice that these guys have the same exponent A1 plus B1, and that exponent is bigger than any other exponent that appears. So that means that the leading coefficient of this guy is what I want. It's A plus B, right? So I have produced A plus B as a leading coefficient of something. I need to justify that this something is in my ideal. But F is in the ideal, and G is in the ideal, and it is an ideal, which means that any combination of F and G is in the ideal. So I'll see of this thing, which is in I, is A plus B, and that means that A plus B is an element of leading coefficients of I. So that's why, for example, this set LC of I is closed under addition. What else do I have to justify? I have to justify that it's also closed under subtraction, but you can see that the same argument works for subtraction. And I have to show that it's closed under multiplication, not only within I, but also when you multiply by something that is not in I. So let's do that. So for example, let's say that I have something which is an LC of I, and I take some other ring element which is not necessarily in this LC of I, it's in the ring. Then I need to justify that A times R is going to be a leading coefficient. But that's easier actually, because if A is a leading coefficient, then I can write a polynomial like this. Okay. And now I want the polynomial whose leading coefficient is R times A. All I have to do is multiply this polynomial by R, which is just a scalar here. So RF is equal to RA x to the A1 plus smaller things. And so that means that RA is a leading coefficient. Closed under addition, closed under subtraction, closed under multiplication by things in the ring, that means that this thing is an ideal. So I have my claim that this is an ideal. Any questions about that little proof? Now, why is that useful? Well, the thing is that we have to use the hypothesis that R is Noetherian, which means we have to apply to some ideal, and we just produce an ideal. Okay? So, what I want to say then is that, sorry, this is kind of a mess, but we did this, and we used that to get to this claim. But the point is that this is an ideal in R. R is Noetherian, so that means that this guy is going to be finitely generated. And so let's say that it's generated by A1 up to AN, which are elements of R. So I have generators for this guy, and somehow I want to use them to get generators for my ideal I that lives inside R of X. So how am I going to do this? Well, what I'm going to do is the following. I'm going to say that because these guys live inside here, they're leading coefficients of somebody. So I'm going to write some polynomial. I'm going to let AI be the leading coefficient of Fi. So Fi is going to be some polynomial whose leading coefficient is AI. Let's say that the degree is EI, and then smaller things. So AI is the leading coefficient of Fi, and then I'm going to define a number n, which is going to be the maximum of these degrees. And you'll see why I do that in a second. Now, but you can kind of see where I'm going. The point is that these AIs are generators for my coefficients, and the idea somehow that I want to think of these polynomials as being generators for my ideal of polynomials. But it turns out that these Fi's are not enough. I need some more. So I'm going to define something else called LC of ID. This is going to be the set of leading coefficients of polynomials in I of degree E. to add 0 to this. So you look only at the polynomials of degree d, you look at all those leading coefficients, and then the claim is that this is also an ideal. It's an ideal in R. How do you prove this? You prove this in exactly the same way that I did it for LC of I. And the reason that I want to do this is because, again, because R is Noetherian, I can say that this ideal is finitely generated. I'm going to say that it's finitely generated by education is going to get a little bit ugly because these numbers depend on D. So I'm going to say that it's finitely generated by the elements BD1, BD2, up until B, D something, which I'm going to call it N there. Here, N depends on D, so I'm going to call it as D. So these guys are generators for LC of ID, and I'm going to replicate what I did there. So I'm going to say that this guy B sub DI is going to be the leading coefficient of some polynomial that I'm going to call F sub DI. This polynomial is B sub DI. Now here, I know that this guy is of degree D. So I don't need an extra variable here. I know that this polynomial has degree D. So through this procedure, I constructed a bunch of polynomials that I called Fi, and a bunch of polynomials that I called Fdi. Now, I'm going to claim that these polynomials generate I. I is generated by the polynomials Fi and the polynomials Fd, comma I. Now, let me ask you, will I be done if I show this? We were looking for generators for I, and I produced a list here. The question is whether this list is finite or infinite. If it's finite, we're done. If it's infinite, we're not done. Now the Fi's go from, the A's go from 1 to n, so the Fi's also go from 1 to n. Now the Fdi's, for each fixed D, the I's are ranging between 1 and the number ND. So for each fixed D, there are finitely many of these guys. But the problem is that D is just some number that I haven't said anything about. And so D ranges from 1 to infinity so far. So this is actually an infinite list of polynomials. But that's why I define this number n, because what I claim is that it's enough to do this for D between 1 and n. If I do this, then I will have produced my finite list of generators for my ideal I. So this will do it. This will show I will be finitely